Root locus analysis, example 11. So we're going to continue to do examples to give you more confidence in doing problems like these. In this case, we've got a little bit more complicated block diagram in terms of the functions that are in the blocks. In this case, we've got a g of s, which has a third order term in it. And then we've got a non-unity h of s. But not to worry. I mean, we're going to just continue to follow the same process that we did before in the same order. And the only difference is maybe there'll be a little more algebra and a little more calculations that we'll need to do. First of all, we're going to find the open loop transfer function. And again, that's kgh. So kgh. And in this one, you notice that kgh are not necessarily in the spots you would expect. Not to worry. Basically, it's the open loop transfer function is just, whatever's in this forward path multiplied by whatever's in this loop back. So we'll go ahead and we'll just write that in. So 1 over 1 plus 0.2 s times 5 over s squared plus 4s plus 9 times k. And I'm going to make a little bit of correction. I'm going to just give this a lowercase k. So k times 1 plus 0.4 s all over 1 plus s. So the first thing that I want to say is that this term right here and this term right here are not in the standard form. Okay, it's not a problem really, but in order to find s's, or excuse me, find poles and zeros, or in other words roots, typically we want them in a little bit better form. So as we move forward, we'll make a few changes to make that so. So for example, if I multiply, and I'm going to do this in a different color, maybe green. If I multiply 5 over 5 here, that makes the numerator, so I can do that, right? Because I'm just multiplying by 5 over 5, which is just a fancy version of 1. So I have 5 in the numerator, and then in the denominator, I'm going to have 5 plus 0.2 times 5, which is 1. So it's going to be 5 plus s. So I'm going to go ahead and rewrite that one. So that's going to be 5 over 5 plus s, and I'm just going to reverse it and put s plus 5. Okay, so this term right here is the same as this right here. Then we're gonna write this next term in. So that's just gonna be 5 over s squared plus 4s plus 9 times, and then we've got a similar problem here. We've got this 0.4 there, and there's there's lots we can do with that as well. One of the things is we can multiply this by or we can factor out a 0.4 on that. So let's do that. So the denominator is 1 plus s. I'm going to just turn that around and make it s plus 1. a little easier to read. And then the numerator, if I factor out that s, or that 0.4, excuse me, I'm gonna have k times s plus 2.5 and then a 4 out front. So, and you can work that through on your own, but that makes the expression a lot easier to deal with. And it's very easy now to see the poles and zeros. We see a pole at -5, we see a pole at -1, we see a 0 at -2.5, and this is going to have a complex number associated with it, and we'll figure that out shortly. So the root locus gain, capital K, if we look at that, it's going to be, and I'll use a different color, I'm going to use green, the 5, 5, and the 4K. So the root locus gain is going to be 5 times 5 is 25 times 4 is 100 little k. So all right. So we now have the open loop transfer function, and then we can take this guy and we can use it to find our closed loop transfer function. And I've gone ahead and provided the first part of that, 100k times s plus 2.5 over s plus 1 times s plus 5 times s squared plus 4s plus 9 plus 100k s plus 2.5. And if we were to take it one step further, we would have 100k little k times s plus 2.5 all over s to the 4th plus 10s cubed plus 18s squared plus 56 plus 100k times s plus 250k plus 45. So, kind of a, complex looking thing. It's a 4th order. So that means the number of poles is going to be 4. We've got 1 0 there. So zeros. Number of zeros is 1, and it's at -2.5. And the number of poles is 4. And and we can see them, actually we can see some of them. Now this one right here, we can't figure that one out without using quadratic expression, but the others are easy. We've got a pole at -1, we have a pole at -5, and turns out we have poles at -2 plus or minus j 2.236. And, I'll just put here, use quadratic. So I'm not going to bother showing that. You know how to use that. Shouldn't be a problem for you. And then once we have that, then the number of branches, same as the number of poles of the open loop transfer function, 4. So that's where we're going to have, that's the branches we're going to have. Okay, so let's continue. So the next thing is just to draw the pole zero map. and plot our poles and zeros. So looks like we go up to a maximum of 5. So I'm going to make this a little bit bigger. 1, 2, 3, 4, and -5. And then 2, 3, 3. So again, imaginary and the real axis. And then let's go ahead and put in our poles and zeros. So we've got a pole at -5. We have a pole at -1. We've got a 0 at -2.5, so 1, 2.5, so it's right there. And then we've got 2 poles at -2, so it's going to be, I better just make this a little bit thinner. So and it's -2.236. That's about 2.25. So -2 is right here, and then this is plus j. This is plus 2j. So it's going to be right about there. And similarly, this is going to be right about here. Okay, so there are our two, our 4 poles and our 1, 0. Okay, so now let's determine where the branches are. We know there's going to be, we know that there's going to be 4 branches. Okay, so is there going to be a branch here? The answer is no, because there's 0 poles and zeros to the right of that. Is there going to be branches here? Yes, there is going to be a branch there because there's 1 pole to the right of this green branch. Okay, what about here in yellow? No, because there's 1, 2, which is even, 2 poles plus 0 zeros to the right of the yellow, so that's not going to happen. And what about here? And that one actually does exist because there's a pole, a 0, and a pole. That's 3 to the right of it, so that one does exist. Now, that's only 2 branches. We know that there's going to be 4 branches total. So in between, in this green branch, that's going to be 1 branch because the pole, it's pretty clear that this pole is going to go towards this 0. And this pole here in yellow, that's just going to go to the left and keep going towards infinity. So the other 2 branches are not on the real axis. They're going to be associated with these 2 poles. So we'll get to those shortly, but let's continue by finding the asymptotes and the breakaway points. So I'll scooch this up, and here are the asymptote formulas. So there's the general formula, and then we've got, whoops, sorry, we've got 4 poles, one at -1, one at -5, and then notice that these are both -2. That's the imaginary poles, and when we're finding asymptotes, we only use the real part of the imaginary poles. So both of them are -2 plus or minus something j. So those are both included there, and then minus the 0 at negative 2.5. Then over the number of poles minus the number of zeros, which is 3. So negative 1 minus 5 minus 2 minus 2 is negative 10. Minus a negative 2.5 is a plus 2.5. And that gives us negative 7.5 over 3, or negative 2.5. So the asymptote is right on negative 2.5. So just to remind you, this 0 is right at 2.5, negative 2.5. So the asymptote is going to go right through that. It's not a problem. Doesn't affect anything other than they're right on top of each other. Then the other thing, the other part is the asymptote angle. We'll use gamma. Same formula as before. This is the ultimate formula once we divide 180 by 4 minus 1, which is 3, so that gives us 60. We can find, putting in 0 for n, that gives us plus or minus 60. Putting in 1 for n, that's 2 plus 1 times 60, which is going to be 60 times 3, which is 180. So plus or minus 60, plus or minus 180, and then it repeats. So again, once it starts repeating, you can just stop. Now, I'm not showing it, but definitely what happens if we put in 2 for n, that's 2 times 2 or 4 times 5. So 5 times 60 is 300. So that's where it starts repeating. So these are unique. Okay? Then the breakaway points. Same formula as before. It's more complicated because it's got an additional, it's got 4 poles. It's still 1, 0 like the last problem, but it's got 4 poles, and 2 are identical because those are the 2 imaginary. And again, for these calculations, we don't use the imaginary part. So those 2 are combined together to form that. And then, like before, I traded in all my sigma b's for x's, and I found this to be my my three potential breakaway points. Now, let's just keep these breakaway points in mind. But let's go back up here, okay? And I'm gonna go ahead and make it a little bit bigger so that you can see things a little bit more clearly. And I'll use a different color. Say I'll use green, and I'll make it a little bit bigger. So those 3 values for the breakaway point we're at -3, so -1, -2, -3, so it's right there. -1.38, so -1.38 is probably right about there. And the other one is at -3.62, so that's right about here. Okay? But where are the branches? We know we have a branch here, and it's going to start at the pole at -1 and go to the 0 at -2.5. So there's no breakaway that occurs there. So that green dot that's right here, that's a, we don't need to worry about that one. I probably should use an X there. But that dot right there, that doesn't represent a breakaway point. We also know that there's a branch that goes here, and it goes off to infinity. Well, that doesn't include those 2. So it turns out no no breakaways occur on the real axis. So even though that formula gave us 3 different breakaway points, they aren't applicable because of the geometry of this problem. And that can happen. So you've got to, you can't just simply look at these numbers that are provided for you and say, well, then they must exist. You have to look at them and see if they make sense for the problem. So just a tip for you, and I'm not going to spend more time on it than that, but it does kind of let you see that there is, sometimes you're going to calculate things that aren't going to be useful to you. Okay, so now we have everything we need, and I'm going to go ahead and draw the root locus based on these, the geometry we have here. Okay, so and again, I'll zoom in on this. Okay, there we go. All right, so to start out with, let's go ahead and draw the asymptote. So it took place right at negative 2.5, and the angle was 60 degree, plus or minus 60, and plus or minus 180. So, and I can write that here. So sigma sub A equals negative 2.5, and gamma was equal to plus or minus 60 and plus or minus 180. Make that a little smaller. Okay, so from this point, we have an asymptote that goes this direction, and we've got one that goes this direction and this direction. Okay, this is 60 degrees. This is 180 degrees. If I went the other way with the 180, that'd be like plus 180. If I went the other way, that would be minus 180. And I'm going to erase all this in a second. And then this right here is minus 60 degrees. So we've included all the angles. Okay? I'm going to get rid of those, the angle and the numbers of the angles. Okay, but there's our asymptotes. And then the breakaway point doesn't matter. So now we can go ahead and draw in our actual branches. So we'll use pink, and we'll make this work pretty good here. So we'll start out. There's a branch that goes there, and it does that. We've got another branch that follows this asymptote and goes off to infinity. And then there's these two floating out in space. So those are gonna, this is one of those where if you've never seen it done, you'll not know how to handle them, but this is the first location of the pole, and then when the pole starts to move, it's going to do this. And that one's going to do the exact same and head down there. So these poles here are just fine as we change the root locus gain. These two, if the gain gets too big, we can see that this pole moves to this side of the imaginary axis, which is unstable. So there is a value where this system gets worse and worse. So we don't want K to get too big, the root locus gain to be too big, otherwise we're going to have an unstable system. As it stands right now, all 4 locations of the poles are, at K equals 0 are just fine. And we can even let K get a little bit bigger and it will still be fine. But if we let the root locus gain K get too large, we're going to be moving into the unstable side of the pole 0 map.